In the last lecture module, we laid out our entire formal system. We distinguished the elements of a categorical statement. We specified 3 different quantifiers, all, no, some. We specified 2 different copula, are and are not, and then we specified how we would represent our subject classes and our predicate classes, and we do that in a way that had a specific relationship. Subject classes are being included in or excluded from our predicate classes. With those elements then, we specified 4 standard form categorical statements: a universal affirmative, a universal negative, a particular affirmative, and a particular negative. And we said that we would spell out our whole logic with just those 4 standard form categorical statements together with their denials. In this module, we're going to turn our attention to our effective decision procedure. Our effective decision procedure is going to utilize Venn diagrams. We're going to graphically depict what at minimum has to be true to make our premises true, and graphically depict what at minimum has to be true to make our conclusion true. And then we're going to check those 2 diagrams in order to decide whether or not this argument satisfies our definition of validity. Recall our definition of validity says if the premises are true, then the conclusion has to be true. So we'll have to learn how to diagram out what at minimum has to be the case in the world in order for each of our standard form categorical statements to be true. And we'll have to depict graphically what has to be true out there in the world in order for the denial of our standard form categorical statements to be true. At that point, we'll be ready to test direct inferences for validity, an argument with a single categorical statement as a premise and a single categorical statement as a conclusion. When we're done with that, then we'll turn our attention to the traditional square of opposition. We'll see that the assumption that classes have at least one member introduces 3 other necessary logical relationships holding between various of those 4 standard form categorical statements. And so if the Aristotelian assumption is true, a much richer set of logical connections will apply. Let's take a look at how we use our Venn diagrams to graphically represent the relationships between our subject and predicate class so that we can represent what minimally has to be true in the world in order for this sentence to be true. So we take a circle on the left-hand side of our diagram. That will be the circle for the subject class. And we'll take another circle on the right-hand side of our diagram. That'll be the circle for the predicate class. And we'll overlap them like this so that area 1 will be the area where we put stuff that is S and only S, only in the subject class, not in the predicate class. Area 2 is only in the predicate class, not in the subject class. Area 3 is in both classes. So something that would be in both the subject and the predicate, that would go in area 3. In area 4, that would be where something that is in neither the subject nor the predicate class would go. We can think of this in terms of our laundry. These are our all white socks. These are our all black socks. These are our laundry day mismatching socks. And area 4 there is I forgot to do laundry day bare feet. Now, let's see how we use those Venn diagrams to depict what minimally has to be true in the world in order for that standard form categorical statement to be true. When we want to depict what absolutely minimally has to be true in order for each of our standard form categorical statements to be true, then we'll use our Venn diagrams to depict what has to be true about the world if a standard form categorical statement is true. So let's look at our first standard form categorical statement, that type A statement, that universal affirmative statement, all dogs are mammals. If that is true, then at minimum, since we're being good Booleans and we don't know if there are any members of our subject class, we don't know if there are any members of our predicate class, what absolutely has to be true if this statement is true, even under those circumstances, is that every member of S would also have to be in P. And so that area there that is S and only S, area 1, that would have to be empty. We go over here and we shade in area 1. This indicates nothing can go in there. That area is totally empty. We empty it out, we turn off the lights, we lock the door. That has to be empty. So no matter what classes we're talking about, if our universal affirmative statement is true, what has to be true about the world at minimum is there can't be any things that are S and only S. That is, there can't be any things that are S and not P. Members of the subject class and not members of the predicate class. That area has to be empty. So we shade it off. What about our universal negative? Our universal negative says no members of our subject class are members of our predicate class. We're being good Booleans. We don't know if there's any members in the subject class. We don't know if there are any members in the predicate class. Here's what we know. Nothing can be both a member of the subject class and a member of the predicate class if that universal negative standard form categorical statement is true. And so once again, we go to that area on our Venn diagram and we say, okay, we don't know what else might be true or not true, but that area has to be empty. We're going to shade that area in, turn off the lights, lock the door, and it's done. Has to be empty. Shading is empty. We already see a trend. Universal statements are going to introduce shading. What about our particular statements? There's at least one thing. It's a member of the subject class and a member of the predicate class. So we'll take an X here. That'll be our one thing. Stand in for our one thing. And we'll say there's at least one thing. Call it X. It's in the subject class and it's in the predicate class. And that's all I need at minimum for that statement, some SRP, to be true. Finally, our particular negative. There's at least one member of our subject class. It is not a member of our predicate class. So we take our X, our one member, and we put it in S and only S right over here. And so now there's at least one thing. It's an S. It is not a P. So again, we see particulars. Some statements introduce X's. Universals, all no statements, introduce shading. What do we do when we have a statement, premise, or a conclusion that says this standard form categorical statement is false? Well, let's say we've got that universal affirmative statement, and our premise actually says that standard form categorical statement has to be false. Then we go, okay, well, in order for that standard form categorical statement to be true, there can't be anything in this area here, in area 1. Nothing can be an S that isn't a P. All the S's, if there are any, they have to be over here. This area has to be empty. That's what has to be true at minimum for our universal affirmative statement to be true. If our premise or our conclusion says that universal statement is false, then we just make sure that that can't happen. So it's false that all S are P. We can diagram that on our Venn diagram by putting an X in that S and only S area, guaranteeing that it's not the case that everything that is an S is a P. We're now in a position to see exactly why those contradictory relationships hold. When we look up here at our universal affirmative corner of our modern square of opposition, we see that it takes this to make our universal affirmative true. But if our particular negative is true, this has to be false. And if this is true, that would mean this would have to be false. I can't have both a member in this area and no member in this area. And the same thing for our particular affirmative and our universal negative. Our universal negative says, look, in order to be true, I can't have anything in this intersection. There can't be anything that's both S and P. And this says, hey, in order for me to be true, there has to be at least one thing that is an S and a P. So if this one's true, this one's false. If this one's true, this one's false. The contradictory relationship holds necessarily between these standard form categorical statements. I'll make one last observation and then we'll end this module and finish up this lecture on the next module. When we think about what we have to do to draw a Venn diagram for a premise or a conclusion that asserts that a standard form categorical statement is false, we can just use the contradictory Venn diagram. If I want to draw a diagram for all S or P, I would draw this diagram. But if I want to draw a diagram that says it's false that all S are P, I draw this diagram. This one says in order for me to be true, this has to be empty. So all S are P, only true if that area is empty. So how do I draw a diagram to indicate what has to be true out in the world? If it's the case that the statement all S are P is false, I make sure that area can't be empty. Same thing in the other direction. Some S are not P, there's at least one thing. It's an S, it's not a P. That's how I make this true. If I have a premise or a conclusion that says it's false that some S are not P, then I go to my contradictory diagram. If my some S are not P needs an X to be true, then it will be false if there can't be an X there. So the contradictory relationship is how I can figure out, if I need to, how to draw a Venn diagram for a claim that a particular categorical statement is false in either a premise or a conclusion.